Hello, in this video we're going to see more examples of recursive functions. We're also going to look at the pros and cons of recursively defined algorithms. So let's start with this recursive function. It's called Ackerman Function. It's defined as well a of mn. When m is 0, it's n plus 1. When n is 0 and m greater than 1 is m of n minus 1 and then 1. So you call the function again, but with the input of m minus 1 for m and n make it 1. But if m greater than 0 and n still greater than 0, then you call the function where it's nested as a m minus 1, and for the second part you call again the function a m and then n minus 1. Let's see the term 1, 1. So a 1, 1. So here I have m is 1 and n is 1. That means I'm here. I'm going to call this function here. So we become a 1 minus 1, which is 0, and call again the function a. M is 1 and n is 1, but 1 minus 1 becomes 0. So as you see here, I'm calling this function again. So where m is 1 and n is 0. So this is, the second part, m is 1, that means greater than 0, and n is 0. So in this case, I have to call the function again a, where m is 1, 1 minus 1 is 0, and 1. Okay, so again, we're going to call this function here a, where m is 0, and n is 1. So this is when m is 0. Once m is 0, we're just going to return n plus 1. Or n is 1, so you return 1 plus 1, which is 2. Okay, and now we're going to call the function again where m is 0 and n is 2. Once m is 0, you just return n plus 1. n is 2, that means I'm returning 2 plus 1, which is going to give me the 3. So as you could see, this a11 is a lot simpler. If I go to a21 or a12, it will require more time and more calling of the function a. Let's see, here is the table that I picked from Wikipedia. So as you could see, when m is 1, n is 1, it will return 3. That's what we get. But as you could see, as we move on, it will grow very, very fast. So for example, 4, 4, it will give me 2 to the power of 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 7 times minus 3. So this number is huge. So as you could see, this function grow very, very fast. Well, this function is useful, but not as the function itself, but as the inverse of it. The inverse of this function, which is, I will call it a to the negative 1, mn. The inverse of this function is useful for something called the algorithm that's behind minimum spanning tree. So the minimum spanning tree in graph theory or in networking, it's used to find the shortest path from point A to point B. So even though this looks just like busy work, but the inverse of this function, it has more useful applications. So let's look at this recursively defined operation, such as exponential. So like 2 to the power of n will be, first we know 2 to the power of 0 is 1, so 2 to the power of 7 will be 2 times calling 2 to the power of 6, and 2 to the power of 6 will be 2 times calling 2 to the power of 5, and so on. The multiplication is the same way. You define the m of 1 is 1, and the m of n is you add, because multiplication is just an addition. So it's 5 times m will be calling m of 5 become m of 4 plus 5, and then m of 4 is m of 3 plus m, which is 5 and 5, and so on. So multiplication is an addition. Factorial is the same way. If you know a 0 factorial is 1, and then n factorial become n, and you call again n minus 1 factorial. Let's see how this can be coded. So let's see this recursively defined algorithm. If a recurrence relation exists for an operation, the algorithm for such a relation can be written either iteratively or recursively. So that's what I have here. Two examples. So one example with written with two models. So for example, S1 is 1 and Sn we wanted to return 2 Sn minus 1. So like, let's see if I need, where is S, this is what we did at the beginning of the section. If I need S5, that means I do 2 S4, and then I call again S4 will be 2 S3, and you call again S3 will be 2 S2, and you call again S2 will be 2 S1, and S1 is given as 1. Then you do 1 times 2 times 2 times 2 times 2. So what does it give me? Basically 2 to the 4th power. So let's see this example. So if I call S and then I have integer n equal to 5. So local variable, we have an integer I and current value, which is basically the current value of S. When you have two lines, this is the description of the code. So the computer doesn't read the description. So here is what we have. If n is 1, then return 2. This is a little bit different what I showed you earlier, where I return 1. In here we return 1, so it gives me 2 to the power of 4. But here I'm returning 2. Okay, else I is 2, current value equal 2. So here we have a while loop. While I less than, so we start with I equal 2. So when I less than or equal to 5, so I is 2, 2 is less than or equal to 5, yes. Then current value become current value times 2. So the current value we start with is 2, so 2 times 2, which is going to give me 4. And then I become I plus 1. So I we started with 2 is going to become 3 now. So, and then I'm still in this loop. So the next thing is 3 less than or equal to 5, yes. So the current value, which is 4, become 4 times 2, which is 8. Now I become 4, increase by 1. Then I go back here. So again, is 4 less than or equal to 5, yes. So the current value become current value times 2, which is 16. And then increase I by 1, which gives me 5. So the while loop gives me 5 less than or equal to 5. So the current value of 16 become current value, which is 16 times 2, it's 32. So you increase I by 1, give me 6. Now is 6 less than or equal to 5? I would say no. So I exit this loop, and then we return the current value of 32. So basically what I returned is 2 to the power of 5. So this is how you find the exponential function with the sum value, for example 5 when the base is 2. So this is how it's coded iteratively. So for the recursive definition, if n is 1, then you return base, you return 2, else you return 2 times s minus 1. So let's see this with the same thing. N equal to 5, so return 2 when n is 1, else you return, so 5 is not 1, so we're gonna go to the else, and we're gonna return 2 s of 4, and then call s of 4 now, and call the function where n is 4, and then n is not 1, n is 4, then you return 2 times s3. Now you have 3, you call in the function, n is not 3, so you go to the else and you return 2 times s2. So calling the function now with the input of 2, so n is not 2, n is not 1, so n is 2, else you're gonna return 2 times s1. Now n is 1. Now if n is 1, return 2. Okay, we return 2. So, and then once it returns this 2, it's gonna multiply that value with the 2, and multiply with the 2 and 2 and 2, which is gonna give me 2 to the 5th, which is 32, and that's what the function gonna return. So the difference between this code and this one, the iteratively computed value of Sn and recursively calculated Sn. So advantage of the recursive is that simplicity of code. So as you see, very few lines of code, and so it's easy to understand more or less. But the disadvantage of the recursive is that memory. So when you call the function and wait call, and all this data right here needs to be stored somewhere, so you need memory. And the speed, it takes longer because it's called the function and wait and call and wait until the last step, and then do the calculation at once. And possibly redundant work. Sometimes it could be very redundant work. So these are these pros and cons for programming using recursive definitions. So right here I have these two examples. So if s is 4, so right here we have these two examples. What does the following recursive function do? If n is 4, so we're starting with n equal 4. If n is 1, return 1, else return 3 s. So we said n4, so it's gonna return 3 s3. You call back s3, you go, and it's gonna return 3 times s2. Call back s2, and it's gonna return 3 times s1. Now n is 1, so we will return 1. So what I have here is 3 to the power of 3, 27. So this other example right here, we're starting with n equal to 5, and then if n is 1, then return 1, else return s of n minus 1 plus s of n minus 1. So it's gonna call s4 plus 4, and then calling the function s, you go back and you're gonna go to the else, and then you call this, gonna give you 4 plus s3. So it's gonna give you s3 plus 3. Calling this function again, when n is 3, it's not gonna go to the if, it will go to the condition with the else. So s2 plus 2. Then when n is 2, it's gonna call and go else, and then do s1 plus 1. And then when s is 1, s of n1, so when n is 1, it will return 1. So basically what I'm returning is 1 plus 1. So this 1 plus 1 plus 2 plus 3 plus 4, which is 11. And this is how we trace s of n using recursive definition. I hope this is helpful.